So here's a diagram of the system I showed in the video. We can see here that we have two pendula coupled together by a spring, and we let L1 and L2 be equal, as well as M1 and M2 are also equal. Now, L1 and L2 consist of bamboo skewer rods. M1 and M2 consist of drill bits. Now, I'm going to approximate those later as just two rods of different linear mass densities, and that's completely fine, and it ends up giving a pretty accurate result. So to describe the system, I'm going to use Lagrangian mechanics instead of Newton's three laws of motion, just because it's easier. So we start off with the total kinetic energy of the system being equal to the sum of the two rotational kinetic energies of the two pendula. Then we look at the potential energy. We see it's a sum of the two gravitational potential energies of the two pendula, and we're taking the zero of the potential energy to be the level where the top of, or the connecting point of those two are, so like where the spring is, where the rod that the spring is on is at. And we have to, of course, find where the center of mass is for each pendula. And doing this was kind of difficult, but all I did was I balanced one of the pendula on a rod and found where its center of mass was that way, where the torques canceled out. And then we have an additional term here which represents the potential energy stored in the spring due to rotation. I'll get into this more, but basically a spring that is rotated provides a torque that is proportional to the angle displaced. So then we write down the Lagrangian, and we write down Lagrange's equations of motion. We get the first equation, then we get the second equation, and then we solve for theta 1 double dot, or the second temporal derivative of theta 1, and the same for theta 2. And also notice here that I made a small angle approximation for sine of theta 1 and sine theta 2, simply so we don't have to solve a nonlinear differential equation, which would be a mess, to say the least. And the result is here. So we get a sum of two sinusoidal functions that are at different frequencies. Right off the bat, we note something interesting. If we let C2, we make C2 equal to 0, we get theta 1 and theta 2 oscillating at the same frequency at the same amplitude. If we make C1 equal to 0, we get theta 1 and theta 2 oscillating at the same frequency at opposite amplitudes, so they're phase shifted by 180 degrees. So now in the video, as you just saw, in order to measure this rotational spring constant, what we're going to have to do is take a spring, attach a lever to it, and a mass, and determine what the torque is due to gravity on the system right here, and then solve for kappa. This wasn't too hard actually, but the way of doing this was so rudimentary, I'm really surprised it gave an accurate answer in the end. We can see in the second term here for the mass of the bob, I used the parallel axis theorem. So finally we arrive at our general solution. We see here that we end up getting theta 1 is equal to the initial angular displacement multiplied by cosine of 7.03t, and theta 2 is the exact same. So what this tells us is that if we start both of the pendula at the same angular displacement, they both oscillate with the same frequency at the same amplitude in phase together. So here's a video of that now. So what's kind of crazy here is that with literally estimating masses and stuff like that based off of lead pellets and converting how many grams are in a grain, etc., that type of stuff, and using really, really rudimentary techniques to measure mass and also the rotational spring constant and the moment of inertia, we see here that the calculated period and the measured period are almost the same. The measured period was done by letting the system oscillate at this particular mode and then counting the number of periods that occur in a certain number of time, dividing it to get what one cycle would be, how many seconds one cycle would be. So this is surprisingly accurate for what it was. So here's a graph of the solution right here, and we see that the superposed together. So this is the angular displacement versus time. We get literally the same graph. We get the solution that theta 1 oscillates at a different angular frequency this time, and theta 2 oscillates at the same angular frequency, but they oscillate 180 degrees out of phase. Honestly, surprising again to see that the calculated period was 0.74 seconds and the measured period was 0.67 seconds. Surprisingly accurate again. So here's a graph of the angular displacement versus time of theta 1 and theta 2, and you can see that they oscillate at the same frequency with the same amplitude, just 180 degrees out of phase. I'll show a video of that now. So now we get to the interesting one that we want to know, and this was the solution I showed at the beginning of the video. If we start one pendulum at an angle of theta naught and we leave the other one where it is, so we start it with no amplitude at all, this is what the solution ends up being. Here's a time lapse of me solving for this solution. And you get here that theta 1 and theta 2 oscillate at the same frequency, but the amplitude of either oscillation is sinusoidal with the same frequency, but 180 degrees phase shifted. So I'll show you what this graph looks like in a second. It's actually really interesting. So we look right here, and we see that the amplitude of, this is theta 2 for right now, oscillates at some frequency. It's sinusoidal, but then within that envelope, each one oscillates with a higher frequency. And of course, here's theta 1 also. So, and again, right here we calculate the beat frequency, and the beat frequency is the frequency of the amplitude envelope to be 8.85 seconds, and we measure the beat frequency to be 8.11 seconds. And again, that's not bad for what I measured stuff with. So I'll call that a success. So here's theta 2, here's theta 1, and here they are superposed together. So this is exactly what we observe when we let the system oscillate this way. We see that we start theta 1 off with its maximum amplitude, then it begins to die down and it stops. Then we look at theta 2. Theta 2 starts with zero amplitude or zero angular displacement, and it begins to rise up, and then it goes and it stops. And this phenomena switches back and forth every time. I think that's pretty incredible that you can get a solution to the system that exactly matches what happens in real life. Now, what this really is right here is a superposition of those two initial modes that I gave you. So the first mode is they oscillate together at some frequency, and the second mode is they oscillate 180 degrees out of phase at a different frequency. If both those modes exist at once, you get what's called beats. and you get this sinusoidal envelope where the amplitude of its oscillation goes up and down periodically. I think that's quite amazing. I hope you enjoyed. Here's the video one.